Moving on to acoustic grating. So this is a little more scientific way of calculating the wavelength and hence the velocity. So what you do is you have a laser beam. You first converge it using one convex lens and then make it a parallel beam using another convex lens. Why do we do this? Laser beam is already parallel. Why do you want to converge it first and make it parallel again? Because you need a specific width. And laser comes in its own width. You cannot directly make it a thicker beam or a thinner beam. So you use two convex lenses to converge and diverge and make it of the width you want. Then you put it inside some material. Now what is this material? It could be just any piece of metal or block or something. The medium in which you want to determine the ultrasonic velocity. And at one end of that material you have a reflector, the other end you have a transducer. Again, inside your waves are going to go and come back in the form of nodes and antinodes. Again, like I said, at the nodes the pressure and density are high, at the antinodes they are low. So what happens is the high pressure areas, that is the nodes, they sort of absorb all the light waves to themselves. So when you put a sheet or screen over here, what output you will see is at the regions corresponding to the nodes you will see a spot of light, and at the regions in between it will just be blank screen. So this is what we call an interference pattern in your photoelectric effect. I don't know how many of you remember that from 12th standard, so I'm not going to go into that. So what happens is you take a laser beam, you converge and diverge to make it of a particular width, then you put it through a material. Inside that material, using a transducer and reflector, you are passing ultrasonic waves which travel like nodes and antinodes. So at the nodes the pressure is high. So outside of that material, when you are putting a screen or white sheet of paper here, you will see a spot at every location which corresponds to the node. Now using this you can find out the wavelength. But again, for that we have an equation, d sin theta equals n lambda laser. This is called the grating equation. So what are these quantities? D is the distance between any two light spots on the paper. Sin theta is the angle between those two rays. For example, if I am taking the 0th and 1st spots, the distance between them is d, and the angle between those two rays is sin theta. N is the order of the spot. Order meaning first spot is first order, second spot is second order, and so on. And lambda laser is the wavelength of the laser light. Now a lot of us get confused between lambda laser and lambda ultrasonic. By the way, this lambda AC is supposed to be lambda US, lambda ultrasonic. She called it acoustic because the experiment is known as acoustic grating, but we are dealing with ultrasonic waves, so it should be lambda ultrasonic. Anyhow, the point being, lambda laser is the wavelength of the laser light we use. Lambda US is the wavelength of the ultrasonic wave. This one is known to us already. When you pick up a laser, it has information about its wavelength. This one is what we are trying to find out. Now, d sin theta n equals n lambda. This is an experimentally determined grating equation. But what we need is not lambda laser, we need lambda acoustic. So how do you get that? Now we saw that this d is the distance between two nodes. But we also saw that if you take twice of such d, which is the distance between three nodes, that is what our lambda ultrasonic is, right? So basically d equals lambda by 2. How did we get that again? Distance between two consecutive nodes is what we call d, and distance between three consecutive nodes is lambda. So d equals lambda by 2. So now lambda by 2 sin theta n equals n lambda laser. So from this you get an equation for lambda acoustic, and once you get the equation for lambda, velocity is simple. You simply plug in the frequency and multiply.